Okay, so I want to say a little bit about something that you might remember from probably your differential equations class. It's called the Dirac delta function sometimes, but it's actually not a function, as we will see. So remember the Dirac delta function. The Dirac delta function, I'm going to put quotes here, satisfies the following properties. One, the integral from minus infinity to positive infinity of delta of x dx is equal to 1. 2, the integral from minus a to a, actually, of delta x dx is equal to 1, and this is for all a greater than equal to 0. And 3, if you look at the integral minus infinity to positive infinity of f of x delta of x minus x naught dx, this is equal to f of x naught if f is continuous at x naught. Now, as you might imagine, there's actually no function that satisfies this property. For example, look at this right here. This says no matter how small of an interval I choose around 0, the integral of this thing is still going to be equal to 1. There is no function that satisfies that property. So the Dirac delta function really isn't a function. Instead, it's something called a distribution. Okay, now what does this mean? Well, a distribution is a thing, it's a mathematical object that's like a function in the sense that we can integrate it and integrate f times, this is a function, we can integrate products, we can do stuff like that. We can integrate it, but we can't evaluate it point-wise as a function. So this isn't the strict technical definition or precise definition of a distribution. But a distribution is just a thing that you can integrate. It's only defined in terms of integration. So I know what it means to do a continuous function times a distribution only in the context of integration. If I don't have this integral here, f of x times delta of x minus x naught, it doesn't really make sense. It only makes sense in the context of integration. Now, the reason we like to call this a function, and I'm not going to be able to show this to you, I mentioned in another video, it just takes a little too long. Or there's some things that we don't know. One of the reasons we call this a function is because it's kind of convenient. It behaves in many ways like a function. And a lot of times you'll think about this as a function that's 0 when x is not equal to 0, and it's equal to infinity there. Okay, now again, that doesn't make any sense. And any function that satisfies that property is not going to satisfy these properties. Okay, but it makes sense. It's like saying we're putting an infinite mass there. Another reason that it makes sense is because very often you can view these Dirac delta function as a limit of other functions, but a limit in a very special sense. So as we will see, as we will use, if you look at the limit as n goes to infinity of the integral x equals minus infinity to positive infinity, f of x sine n of x minus x naught over pi times x minus x naught dx, this is equal to f of x naught. So if you compute this integral, it's going to depend on this parameter n and the parameter x naught. If you compute this integral and take the limit as n goes to infinity, it equals f of x naught. So in this way, we can kind of say that the limit of these functions, that this limit is equal to delta of x minus x naught. So in this sense, we see that the limit of these functions is equal to the delta function. And so in that sense, since it is a limit of functions, we kind of think about it as a function, or refer to it as a function, and psychologically think of it as a function. But one thing needs to be pointed out. When we say that the limit of these sine functions is equal to the Dirac delta function, okay, what we mean is that this limit on the outside of the integral, the limit on the outside of the integral, So in other words, these two things are equal to each other. This is equal to the integral of f of x. I'll step out of the way in just a second. X minus x naught dx, and here we're going from x equals minus infinity to positive infinity. So in this sense, we're saying that this function, this sequence of functions as n goes to infinity, converges to the Dirac delta function, but not in the sense that if I take the limit of, if I take the limit of this pointwise, I get the delta function. And the reason is, if I take the limit of this as n goes to infinity, well, it doesn't exist aside from when x is equal to x naught. And even then, we've got weird stuff going on. Okay, so this limit does not exist. As n goes to infinity, this limit does not exist as a function. But this limit does exist as n goes to infinity. This limit does exist as an integral. And so what we say then is that these sine functions converge weakly to the delta function. So since this limit exists, this limit right here, another way to express this limit is to say that sine of n of x minus x naught over pi of x minus x naught converges weakly to the function delta, not the function, but the distribution delta of x minus x naught. Now, technically speaking, like when I write the argument delta of x minus x naught, I'm writing this like it's a function. I'm using function notation. Technically speaking, this doesn't make any sense because delta is a function. We can't evaluate it at points. But all this is to denote is that it is the Dirac delta distribution, which is typically centered at 0. It's shifted over to be at x naught. That's all this represents there. And so sometimes you'll even see a notation like this: delta sub x naught, meaning the Dirac delta function or the Dirac delta distribution centered at x naught. Okay, so unfortunately, I can't talk a whole lot about the Dirac delta function. These are the important properties that we're going to use. Another important property is that we'll see when we do the Fourier inversion formula. Another important property is that the limit is that this limit exists. That the limit of these guys gives us a delta distribution. There are other functions. If you look up like mollifiers, that's another way. I can't think of the other name for them now that I'm trying to explain it. When we get to Laplace equations, we'll look at the Poisson kernel. The Poisson kernel also satisfies a similar property as this. Okay, that's all I'm going to talk about today. Not today, that's all I'm going to talk about for this. I've already made the video on the Fourier inversion formula where I talk about this, but I just wanted to make another video where I talk specifically about the Dirac delta distribution.